my name is Ivan Wyborny, and I am one of the authors of the English version of this course. Previously, we discussed pure and mixed quantum states, gave a definition of density matrix, and defined a separable and inseparable quantum system for both mixed and pure states. Now, we continue our talk on the separability of physical systems and the phenomena of quantum entanglement. And our topic for this lesson is the criteria for pure state separability. We will talk about the so-called Schmidt decomposition. So, let us formulate the following theorem, which is also known as the Schmidt theorem. Suppose a state vector psi sub AB describes a pure state of composed physical system that consists of A and B subsystem. Then, two certain sets of orthonormal states, vector xi sub I and phi sub I for the subsystems A and B respectively exist, so that the state vector psi AB of the whole system can be represented as the sum of the square root of lambda I times tensor product of vectors xi and phi I. Such expansion is also known as the Schmidt decomposition. Any term in this sum has a non-negative real coefficient, i.e. the square root of lambda sub e is a non-negative real number. These coefficients are also called Schmidt's coefficient and obey the following condition. The sum over all lambda I is unit. Let us now prove this theorem. So, we have to prove that the pure state psi AB of a compound system A plus B can be represented as the sum over E square root of lambda I xi IA phi A IB, where xi IA and phi IB are respectively the orthonormal states of the systems A and B. Let's assume for simplicity that Hilbert spaces for A and B have the same dimensions. So dim HA equals dim HB. Let G A and K B be bases for systems A and B respectively. Then we have psi AB equals sum over GK alpha GK GA KB, where alpha GK are the coefficients. Alpha GK equals GA KB and ket psi AB. The coefficients alpha GK form a Hermitian matrix alpha, which could be diagonalized. So alpha equals U D V. Here D is a diagonal matrix with non-negative elements, and U and V are certain unitary matrices for change of basis. Thus, psi AB equals sum over E G K U G E alpha I, since the alpha is diagonal, V I K, and cats G A K B. We can now redefine the basis of A and B in such a way. So let xi IA be the sum over G U G I G A, and phi IB be the sum over K V I K K B. This is just a redefinition of our basis. And now we can denote, since the alpha II are non-negative, we can redefine it in such way. Let alpha II denote alpha II by square root of lambda I. Okay, and what we got now? Actually, we've got the statement of the Schmidt theorem or the Schmidt decomposition. So the CAB equals sum over I square root of lambda I C I A phi I B. This completes the proof. So we have the Schmidt theorem proved. Let us now discuss how to find out whether the pure state is separable or not using the theorem. It's quite simple. Suppose we have a certain physical system and the Schmidt decomposition for its pure state vector psi sub AB. The number of non-zero Schmidt coefficients is called a Schmidt number. In other words, the Schmidt number is the number of terms in Schmidt decomposition. If the Schmidt number is unit, then the pure quantum state is separable, and the composed system's state vector can be represented as a tensor product of state vectors corresponding to each part of the system. If the Schmidt number is greater than 1, then we are dealing with a non-separable or entangled quantum state. For the sake of clarity, let us now prove the following aspect. Of course, in a way, separable states are simpler since they have only two multipliers. These multipliers are two state vectors corresponding to certain subsystems and nothing more. However, in practice, the case of entangled states is of interest. Further detailed consideration will be given in the next lesson. As an example, we will consider a very important case of entangled qubit states that are called the belt states. That's all for now. Thank you for your attention.